What is the energy source of smartphones? Battery, right? Like smartphones, many devices use batteries. Wireless devices have rechargeable batteries. Watches and radios have no rechargeable batteries. So what is happening inside a battery to produce electrical energy as well as to discharge it over time? This is because the battery is an electrochemical cell. In this video, we will discuss about electrochemical cells and some terms related to electrochemical cells. Basically, electrochemistry is the study of production of electricity from energy released during spontaneous chemical reactions and the use of electrical energy to carry out non-spontaneous chemical transformations. The subject of electrochemistry has wide applications. Batteries and fuel cells convert chemical energy to electrical energy, and they are used on a large scale in various devices. Many metals like sodium and magnesium and chlorine, fluorine and sodium hydroxide are produced by electrochemical methods. Also, the transmission of sensory signals through the cells to brain and from the brain to cell are known to have electrochemical origin. There are mainly two basic types of electrochemical cells: voltaic or galvanic cells and electrolytic cell. In voltaic or galvanic cell, chemical energy of a spontaneous reaction is converted into electrical energy, while electrolytic cell use electrical energy to carry out non-spontaneous reactions. In this video, we will discuss about voltaic or galvanic cells. Daniell cell, which was discussed in class 11th, is an example of voltaic cell. In Daniell cell, the overall reaction is Zn plus Cu2 plus gives Zn2 plus Cu. This is composed of two reactions, a reduction reaction and an oxidation reaction. These reactions occur in two different portions of the Daniell cell. The reduction half cell reaction occurs on the copper electrode, while the oxidation half reaction occurs on the zinc electrode. These two portions of the cell are called half cells or redox couples. That is, copper electrode is called reduction half cell and zinc electrode oxidation half cell. Generally, oxidation half cell is called anode and reduction half cell is called cathode. You can remember this by remembering two phrases. One is anox and other is red cat. Anox corresponds to anode is where oxidation occurs. Red cat corresponds to reduction occurs at cathode. At each electrode-electrolyte surface, that is either anode or cathode, metal ions from the solutions have a tendency to deposit on the metal electrode to make it more positively charged. And the metal atoms of the electrode tend to go into the solutions as ions, leaving the electrons at the electrode, making it negatively charged. At equilibrium, there is a charge separation between the electrode and the electrolyte. Electrode may be positively or negatively charged with respect to that of the solution, depending on the tendency of the opposing reactions. Now, a potential difference develops between the electrode and the electrolyte, which is called electrode potential. According to IUPAC convention, when all the involved species have a unit concentrations, then such a potential is called standard electrode potential. Anode is the half cell where oxidation occurs and cathode is where reduction occurs. Anode has a negative potential with respect to that of the solution and cathode has a positive potential with respect to that of solution. We know that there is now a potential difference between the anode and cathode. So there will be a flow of electrons from zinc electrode, which is negative electrode, to the positive electrode, that is copper electrode. The current flow is opposite to that of electron flow. Now let's discuss about cell potential. Cell potential is the potential difference between the two electrodes of a cell. However, when no current is drawn through the cell, it is called cell electromotive force or simply EMF. According to the accepted convention, cells are represented by anode on the left side and cathode on the right side. If you take galvanic cell, the metal and electrolyte solution is separated by a vertical line and two half cells are connected through salt bridge, which is denoted by the double vertical lines. Let us discuss this with an example. Find the expression for cell potential for the following cell reaction. Cu plus 2Ag plus gives Cu2 plus 2Ag. Here cathode reaction is 2Ag plus 2 electrons gives 2Ag and anode reaction is Cu gives Cu2 plus 2 electron. The cell representation is Cu bar Cu2 plus double bar Ag plus bar Ag, as you can see here. We already know that cell potential E cell is equal to E right minus E left, which is equal to E Ag plus bar Ag minus E Cu2 plus bar Cu. The standard electrode potential of an unknown half cell is determined experimentally by combining it with a standard hydrogen electrode. The standard hydrogen electrode is represented by Pt bar H2 bar H+. This electrode is assumed to have zero potential at all temperature according to the reaction H plus 1 electron gives half H2. The standard hydrogen electrode consists of a platinum electrode coated with platinum black. The electrode is dipped in an acidic solution and pure hydrogen gas is bubbled through it. And the pressure of hydrogen gas is 1 bar and concentration of hydrogen ion in the solution is 1 molar. Now let us see how we can use standard hydrogen electrode to measure the electrode potential of zinc electrode. After connecting zinc electrode in zinc sulfate solution with the standard hydrogen electrode, the EMF is measured. Generally, the standard hydrogen electrode is taken as anode, that means reference half cell, and cathode as unknown half cell. So here the cell representation would be Pt bar H2 bar H plus double bar zinc 2 plus bar zinc. The EMF of the cell can be calculated by E cell is equal to E right minus E left, which is equal to minus 0.76 volt. Here we already know that cell potential of standard hydrogen electrode is 0, that is E left will be equal to 0. Then E right would be minus 0.76 volt. This EMF would correspond to the standard electrode potential of the half cell reaction Zn2 plus 2 electron gives Zn. This negative value of standard electrode potential indicates that hydrogen ions can oxidize zinc or zinc can reduce hydrogen ions. Then what will be the standard electrode potential of copper electrode? The measured EMF of the cell Pt bar H2 bar H plus double bar Cu2 plus bar Cu is 0.34 volt. Knowing that the electrode potential of standard hydrogen electrode is 0, we will get the standard electrode potential of copper electrode as 0.34 volt. This positive value of standard electrode potential indicates that copper ions get reduced more easily than hydrogen ions. This means that hydrogen ions cannot oxidize copper, or we can also say that hydrogen gas can reduce copper ion. Therefore, copper is insoluble in hydrochloric acid. Now, we got an idea about standard electrode potential and find ways to measure its values. If we arrange the electrode potentials of some electrodes in a series with decreasing order of their standard electrode potential, we will get electrochemical series as you can see here. Here we can see that the hydrogen electrode has zero potential and others have either higher or lower electrode potentials than hydrogen electrodes. Positive electrode potential means that the redox couple is a better oxidizing agent than hydrogen. For example, in the series we can see that fluorine is the strongest oxidizing agent. Knowing the standard electrode potentials of individual electrodes, we can calculate the cell potential of any electrochemical cells. Then the EMF of the Daniell cell represented by zinc bar zinc 2 plus double bar Cu2 plus bar Cu is given by E cell is equal to E right minus E left. The standard electrode potential of zinc electrode is minus 0.76 volt and that of copper electrode is 0.34 volt. Substituting these values, we will get E cell is equal to 1.10 volt. We have discussed that galvanic cells use chemical energy evolved from the reactions to produce electrical energy. But how do we calculate the maximum energy which can be produced by the galvanic cell? Also, for practical purposes, one cannot use unit concentrations of reactants in electrochemical reactions. So, how does change in concentrations affect the cell potential of the electrochemical cell? Be curious. We will see about this in our next video. With this, I will summarize this video.
Manorama Horizon, learning made simple.